And the difference between a biological and a physical science is that physical sciences tend to focus on the non-living things, right? Biological sciences have to deal with biology, okay, things that are living. So all the plant sciences, all the biology variables, even biochemistry is a little bit leaning more toward the biological sciences, things that deal with living things. Other examples of physical science besides chemistry is physics. That's our other big example of a physical science, right? All right, biological science focuses on living, physical science focuses on non-living. All right, here's your book definition of what chemistry is. So you can shorten it down. When I have things up on the PowerPoint, you don't have to write them down word for word. Please do what is best for you in terms of note-taking, okay? You need to find ways to abbreviate, find ways to speed up your note-taking process. So that's not copying what I have necessarily word for word, all right? So chemistry studies the composition, structure, and properties of matter, the processes that it undergoes, and the energy changes that accompany these processes. Connor, can you see okay?
Yeah.
Behind this podium? Okay. All right, so when we talk about the composition of matter, what do you think that might entail? We think about 3 different types of subatomic particles. The proton, the
Neutron, electron.
and electron. Good, right? Those are things that might compose matter, right? Then we start looking into those a little bit further into the elements, right? Elements are made up of certain numbers of protons, certain numbers of neutrons, certain numbers of electrons, okay? So that composition starts with that main building blocks and can expand to lots of different stuff. Structure and properties of matter are just the things that kind of define what each element is, right? Each different composition, each different compound has a different shape, it performs differently, it has different, what we call properties of matter. We're going to look at properties today, but the way it behaves is different, okay? Each one has its own individual characteristics, just like humans, right? Each of us perform a little bit differently. We have different traits, different characters. Elements kind of go with the same, go with that same movement, right? We've got different characters for all of those. Energy changes that accompany processes. Can anyone think of different types of energy changes or ways that we might transfer energy? Yeah, yeah, heat is a really good example. Anything else? Okay, that's the main thing that we will talk about in terms of energy changes. That's a really good example. Okay, very good. These are a couple different branches of chemistry that we'll talk about. Okay, not that we will talk about, I'm sorry, but that you could explore a little bit further. Okay, organic, inorganic, physical, analytical, biochemistry, and theoretical. All right, so what makes up matter? And how do we define matter? Okay. Everything in this world that contains matter, that has matter, is built from an atom. We've heard the word atom before? Yes, hopefully? All right, good. So the atom is the smallest unit of an element that contains all of those chemical properties. And that last part is extremely important. So you might want to underline that part, that maintains the chemical properties of that element. So if we look just at an element, we can break an atom down farther into protons, neutrons, electrons, but protons don't have any elemental characteristics. Right? Protons are a charge. They don't have any elemental characteristics. Protons don't melt or freeze or things like that, like elements do. They don't have freezing points, boiling points, things like that. Atoms have all of those characteristics of that specific element. So that's important for you to remember. So bigger than an atom is what we call an element. An element is a pure substance, so it's only made of one thing. Okay, it's made up of one kind of atom. That's it, one type. So you should all be familiar with that chart right there, right? Have we seen the periodic table before? Good. Okay, so all of those little blocks, what do they each represent? An element. Okay, and each of those elements have its own characteristics, has its own properties. So elements are made up of one specific type of atom. Okay? When we break down compounds, we reach a point where we can't break them down anymore. Okay? An element can't be broken into other stable substances because it's only made up of one thing. Right? Elements are only made up of one type of substance. So if I've got a chunk of sodium and I keep breaking it down and breaking it down and breaking it down, it's never going to break down past sodium. Right? We're not going to get any smaller than that. Okay? It's always got to be a sodium molecule. All right? Examples of elements, we talked about anything on the periodic table. Carbon, hydrogen, oxygen, those are our main big dog elements, right? We use them almost all the time. But any of those on the periodic table are elements. Okay? But these are just a few examples of that. And now, building on elements, we can build something called a compound. Could anyone give me an example of a compound? Yeah, Rachel.
H2O.
And what's H2O called?
Water.
Yeah, water. That's an example of a chemical compound. Anyone else? Yeah.
Sodium chloride or salt.
Yeah, sodium chloride is salt. What about carbon monoxide? CO, right? And CO2 is called what? Carbon dioxide, okay? All that, everything that you just did right there, that naming stuff, we're going to learn how to do all of that. You guys already know how to do a couple, okay? Those are all compounds. And the reason that they're compounds is that they are made of more than one element, right? They're chemically bonded, and they're made from more than one substance, okay? Compounds can also be made of two atoms of the same substance. Okay, so compounds can be basically two or more atoms. Could be same types of atoms, could be different types of atoms. Okay, so there are a couple more compounds. They can be pretty simplistic like water. They can get really, really, really complex. What if I have this formula right here? This is oxygen gas. Is it considered a compound or not? Yes. And why is it considered a compound? There's two atoms, exactly. Even though they're two atoms of the same element, it's still two atoms. Okay, so if we have two atoms that are chemically bonded, whether they're the same type of atom or not, it's still considered a compound. Does that make sense? Okay, if we can break it down into an element, into a single element, then it's a compound. Okay, so we could break apart those two oxygen atoms into single oxygen atoms, and so that makes it a compound. Okay, so as long as it's two atoms bonded together, Substance made of atoms, 2 or more elements. It doesn't have to necessarily be 2 or more elements. Just as long as it's 2 atoms that have bonded together, we consider that a compound. All right? So we talked about these different building blocks of matter. Now we think about what is matter in and of itself. Okay? So in order for something to be considered matter, it has to take up space, and it has to have a mass. What is kind of the generic term for mass? What might be kind of our slang term for mass? Weight, yeah. Essentially it weighs something. Once we get into physics, those things mean 2 completely different things. But for right now, we can think of it as having some sort of mass or some sort of weight. It might be a really, really, really small mass, but it's a mass, okay? And it's got to take up some space. All right, what about something that has volume? When we say something has volume, that means that it's taking up some 3-dimensional space. All right, so when we're saying that something takes up space, we're saying that it has a volume of some kind. Okay? And just like we're saying, in order for something to be matter, it has to have a mass, and it has to take up space. So it has to have a volume, it has to have a mass, which is basically measures the amount of matter that we have. It's its weight. Okay? So in order for something to be considered matter, it's got to take up space, which means it has to have a volume, and it has to have a mass. Okay, so we just looked a little bit closer at those 2 things. All right, we've looked at basically what matter is, where it comes from, the different kind of stages of that. Now we're going to look at how we can change state, okay, or phase change. I'm going to talk about it like that too. So when we talk about a physical change, we're talking about a change from one state to another state. Okay, and the states of matter or the phases of matter that we're talking about are the solids, liquids, and gases. Okay, so we're going to talk about each of them kind of specifically here. Solids have definite shape and definite volume. Definite shape and definite volume. All right, so my cup here has a definite shape and a definite volume. It takes up a certain amount of space. It has a definite shape. Okay, there's no changing that. If I would set this into a box or something, my cup's not magically going to start reforming to fit the box, right? This cup has a definite shape and a definite volume. Okay, it's not going to start transforming and put it in the trash can to mold to the trash can. Agreed? All right, good. Okay, when we talk about a solid, we have particles that are really close together. Okay, we don't think that solid particles look like they're in motion, but they are. Okay, the particles in this cup that make up this cup are in constant motion. Are they moving a whole lot? No. But they are still in continuous motion. Okay, it might be more of a vibration. We definitely don't feel it, but those particles are in motion. Okay? If they weren't in motion, we'd be in big trouble. Okay? That means we've reached a point that's so cold that our particles can't even move. We'd be long gone. Okay? So in a solid, we don't think that maybe these particles that make up our table are moving, but they are. Okay, they're in that constant vibrational motion. And those particles are really close together. If we had solids that had particles far apart, not really a solid anymore because things could fall through, right? So solid particles have to be close together and they're in constant motion. Okay? Liquid, things that define a liquid. Do they have a definite shape and a definite volume?
No.
No. What do they have? A definite what?
Volume.
Good, very good. They have a definite volume but no definite shape. Okay, so within my cup, as I start to kind of move this around, that liquid is moving around within the cup. It's not gaining liquid, it's not losing liquid unless I spill it, but it is reforming its shape to move around and fit that cup. Okay, so if I would pour it down the drain, which I don't want to do because I want my water still, okay, it's going to start reforming to fit that drain. It's not going to stay in the cup shape as I drop it into the sink, right? It has definite shape but no definite volume. I'm sorry, backwards. Definite volume, no definite shape. It's always going to fill the shape of the container that it's in. So if I dump it into a bathtub, it's not going to look like I have very much water there because it fills the bathtub. But if I have almost a full cup here, it looks like I have a lot, right? So it's going to fill that container as best as it can. Liquid particles are close together, but they have the ability to move and slide past each other. They have a little bit more freedom than solid particles do, right? Do you think liquid particles are closer together or farther apart than solid particles? They're farther apart. They're a little bit more spread. They've got the ability to slide and move past each other. They've got the ability to kind of really relocate. They're still bonded. They still have that surface tension and attraction between molecules, especially in water molecules, but they do have a little bit more freedom than solid particles do. Okay? And gases. What do we know about the shape and the volume of gases? None. No definite at all. No definite shape and no definite volume. Okay, which means they're going to fill the volume and the shape of any container that they are contained within. Okay, so this room is considered to be a container. That means any gas in this room has dispersed itself completely throughout this room. Any oxygen, any nitrogen, any gas that's in here has been dispersed throughout the room to fill the shape and the volume of this container, this room. Okay? Same thing goes within this cup even, right? The little leftover space that this liquid is not filling has been filled with gas. Okay? So it's filling that container within this cup. Our particles in a gas are considered to be far apart. Okay, and we say far apart, we mean relative far apart. So what I mean when I say relatively far apart is that these particles of a gas might be, thousandths of a centimeter apart. But in comparison to a solid particle, they might seem really far apart. Does that make sense? So relative to a solid, gas particles are extremely far apart. Gas particles have the ability to move around in what we consider constant, rapid, random, continuous motion. So a gas particle will move in straight line motion until it hits something. And then it's going to bounce off and move it back again. And then it's going to bounce and move again. And it's going to bounce. Okay, we'll do an entire chapter on gases, but I want you to understand the motion that goes into gas particles. They're moving in constant, rapid, random, continuous motion. Okay, so they're going to move in a straight line path until it runs into something. And then it's going to hit the wall, and it's going to bounce until it hits something else. And then it's going to go until it hits something else. Whether it's another gas particle, whether it's the wall of the container, whatever it is, that particle is going to keep moving until something stops it. And then it's going to bounce off and go again. Okay, so those gas particles are in constant motion. And they have just a little bit more room to spread out. Okay, understood? Very good. Plasmas are our fourth kind of state of matter. We don't talk about it much, but it exists. Okay? Plasma exists at really high temperatures. Really high temperatures. Apparently I can't spell lose correctly. Okay, so it should be lose their electrons, not loose. It's a big pet peeve of mine, so I'm not sure how that got in there. High temperature physical state of matter. So we reach a temperature that's so hot that electrons just start to break down and break off. It doesn't happen that often because it's such a high temperature, but that's what happens at the plasma state. Okay, so we reach a temperature that's so high, our electrons start moving so quickly, they can't stay in balance, they can't stay in that orbit, and they start to disperse. Okay? You can find that in a fluorescent light bulb. Okay, so all of our light bulbs here have reached that point where our electrons kind of start dispersing. Oops, I'm sorry. All right, do we have what we need here? Okay, I just want you to kind of take a look at this. You don't have to copy this chart down or anything. I want to just kind of talk with this. This is looking at water, okay, or H2O and the different states of matter that go with H2O, okay? So we have names for the different phases of water. We don't necessarily have names for different phases of each compound, right? We don't have a different solid name for CO2, just like we have a solid name for water, which is ice, okay? But when we look at solid water, or ice, it forms what we call the crystal lattice, or a lattice. Does anyone know what lattice is, like in your yard, or does anyone know what that meant? Like lattice fencing? Has anyone seen that? Like on decks, you know, on the bottom of decks, you see that crisscross fence. That's called a lattice, okay? And vines kind of grow up these things called lattice. And what that means is that it's basically just this crisscross pattern, okay? And so molecules, when they freeze or when they become a solid form, tend to form what we call this crystal lattice. And crystal lattice is really organized. They form lines, they have bonds and attractions that hold them in that crystal lattice. Okay? So once we reach a temperature so low that our electrons kind of stop trading and they kind of get settled into this place, it's called a crystal lattice. Okay? We warm up to a liquid and we start seeing that crystal lattice kind of break down. We add heat, right? We're adding energy to something, we're heating it up. When we add energy, we can add enough energy to start breaking those bonds, which allows things to kind of melt down to that liquid form. Okay, are we seeing how that's coming together a little bit? Is this all kind of a review? A little bit? All right, very good. And then once we break even those bonds, we form a gas, which means we got more room, no bonds between molecules anymore, no chemical bonds between molecules anymore. And then the plasma state is where things just get crazy. Okay? All right. So we talked about changes of states and physical changes. Now we're going to talk about physical properties. What makes up physical properties and chemical properties? All right, so we looked at the different states of matter that elements can be in. Now we're going to look at the properties that go into these elements. Okay? So physical properties is something that you can measure, something that you can observe. Okay, so these are things that you can see without changing the identity of the substance. Yeah, I'll explain that here in a little bit. These are examples of a physical property. Things like the melting point, the boiling point, color, density. These are all things that you can observe without changing the integrity of our compound. Okay, so I can melt water and then freeze it back and it's still water. Right? It didn't change compounds. I didn't add anything new, take anything away. Okay? But the melting point and the boiling point are temperatures. So the melting point is the temperature at which a substance is going to melt. The boiling point is the temperature at which it's going to start turning into a gas. Does that make sense? Have we heard those terms before? Melting point, boiling point, and freezing point is another one. physical change, that means this is a change in our substance that's not sacrificing the characteristics of that object or of that substance. Okay? Doesn't involve a change in identity of that substance. So that might be a change in state. Things like melting, freezing, boiling, those are all changes of states. That's a physical change. Also things like grinding something up, making it smaller, right? Cutting it into smaller pieces. If I grind it, if I am trying to manipulate it in some way, but I'm not changing the substance, that's what we consider a physical change. Something else that you should note about a physical change is that typically physical changes are reversible. Okay, typically physical changes are reversible. Okay, so that might be something else that you put down. For the most part, physical changes are reversible. With the exception of maybe grinding things up, I can't really ungrind something, right? I can't glue it back together in terms of elements, okay? But if I melt something, I can make it go the other way, and hopefully that substance has not broken down enough that I'm changing the substance. Any questions there about physical? Okay, let's look at chemical. Oh, sorry.
I have a question about if it changes into a plasma, is that a physical or chemical?
It's still a physical. Yep, still a physical. Good. Yep. Because essentially, once we start cooling it back down, it should recollect itself. Yeah, good question. Okay, a chemical property is something that kind of relates a substance's ability to undergo chemical changes. Okay, so here's some examples of chemical properties. Whether things burn, whether they rust, whether things are soluble or not, so they're able to dissolve a substance's pH level. That's a chemical property. If it's reactive with certain things, those are chemical properties. Okay, so it's all about how substances react with one another. That's what determines if it's a chemical property or not. And chemical properties are typically not observable. We can't look at an object and view its chemical properties. Okay? Whereas physical properties are usually observable. We can see them. Okay? All right. When something undergoes a chemical change, that means that we're moving into a new substance. Okay, something has happened, a change has been made in which we're forming a new substance. Okay, when one or more substances are converted into different substances. Okay, chemical changes can be considered endothermic or exothermic. Okay, so giving off heat or taking in heat. Most of the time, chemical changes are irreversible. Okay, so we talked about physical changes most of the time being reversible. chemical changes are most of the time irreversible. Okay, we can't take them back. All right, I want you to look at page 10 if you have your book. Okay, go ahead and open to page 10, and there's an example up here about mercury. So figure 7 on page 10. All right, so figure 7 starts with something called mercury oxide. And mercury oxide is what is in the bottom of that test tube right by the flame. Okay, can we see where that's pointed out at? Mercury oxide. Okay, it's got physical properties that it's a bright red solid. Okay, bright red or orange red solid. Its chemical properties that it decomposes when it's exposed to light or when it's heated to 500 degrees Celsius. Okay, so in figure 7, we see it breaking down to form oxygen gas and mercury. That means from the flame and from its chemical properties, we can assume that it's being heated to 500 degrees Celsius because we see it breaking down. Right? We see it forming that oxygen gas, and we see it forming pure mercury. Right? That silvery white kind of liquid, even though it's a metal. Okay? Do we see that happening? Those little mercury bubbles kind of on the outside of the test tube, and then we see those gas particles floating out. Okay? So this is a chemical change. When it cools back down, it's not going to reform mercury oxide. When it cools down, we're left with mercury, and we're left with oxygen gas. Okay? So that's going to be an irreversible change. All right, there's two parts to a chemical change, and I'm going to show you a chemical reaction. Okay, two parts to a chemical change. When I have a chemical change, I start with something called the reactants. These are the substances that are doing the reacting, right? These are the substances that you start with. Okay, so there's two parts. The reactants are what you start with. Those are the things that are being combined, or at least it might be only one substance. That's what you start with in a chemical change. The products are what you end with. Right? The product is what has been formed. The new substances, or maybe just new substance, might only be one, that's created in a chemical change. So you need to understand that reactants, you might only have one thing, and you're breaking down and forming two things, right? That's the example that we just looked at. Or you might start with two and end with one, or start with two and end with three. There's lots of different combinations you can look at in a chemical change. So don't get hung up with the numbers. I want you to understand that reactants are what you start with, products are what you end with. Okay, are those two terms that you're pretty familiar with, or are those new terms? A little bit of both? Okay, that's all right. So this is a chemical reaction. If you want to write this down as an example, that's fine. That's kind of up to you. This is hydrochloric acid combined with calcium carbonate, and it's forming calcium chloride, water, and CO2. Okay, you don't have to know the names or anything yet, but what I want to show you is that how we separate this chemical reaction. This arrow means, anyone know? What that means? Yeah, it essentially means it becomes, right? The arrow is telling us that's where the reaction's taking place. Okay, so that means these are our starters or our reactants. And this is what we end with, okay, which means these are our products. All right, so anything to the right of the arrow will be our products. Anything to the left of the arrow will be our reactants. Does that make sense? Okay, so the arrow is telling us there's a chemical reaction taking place right here. This is what we end with. This is what we started with. All right? Good enough? Reactants and products. All right, what I would... Little line in there. We talked about properties of matter already. But now we're going to talk about extensive and intensive properties. So we talked about chemical properties and physical. Now we're going to talk about extensive and intensive properties. Just knowing what we know about prefixes, what do we think the word extensive might mean? Outside. Very good. So an extensive property is something that we can view on the outside. So it depends on the amount of matter that's present. Extensive properties, they depend on the amount of matter that's present. Okay, so examples of an extensive property might be its volume, its mass, things that make a difference, how much of that object is there, how much of that substance is there, right? If I've got more of my substance, that means I've got more mass. It's going to take up more space, so it's got more volume. That's an extensive property. Okay, the amount of energy that it requires, those are all extensive properties. Intensive properties. So intensive properties, what do you think intensive means?
Inside.
Yeah, inside or within. Okay, so those intensive properties are things that we don't really care how much of that substance is there. It doesn't matter how much of that substance is there because these properties are found within the substance. That means it doesn't matter how much of our substance is present. Okay, these are things like color, density, melting point, boiling point, freezing point, all of those things. But it doesn't matter if we've got two, let's say, 2 red jelly beans or 500 red jelly beans. They're all red, right? So that color is an intensive property. That's kind of a broad example, but each element has its own properties, right? So the color of sodium doesn't change whether we have 2 sodium atoms or 10,000 sodium atoms. Just like the density of water doesn't change whether we have 1 water molecule or 1,000 water molecules. Okay, those are intensive properties. Okay, does that make sense? Okay. All right, so we've talked about all the different types of properties. Now let's look at all of our changes put together now. When we use a physical or a chemical change, we've got to expend some type of energy, okay? Some sort of energy change is required. And that's for both physical and chemical changes. We've got to use some sort of energy. Okay, it can be in the form of heat or light or electricity or any other types of energy that we want to look at. What do you think the most common form of energy transfer is in chemistry? Yeah, heat. We're usually heating things up or cooling things down. Okay, to go through a chemical reaction, we're usually heating things up or cooling things down. So we're using heat as our form of energy transfer. It's important for us to understand that throughout a chemical reaction, energy is never created or destroyed. It only changes form. Okay, and do we know what that little sentence right there, that little gem is called?